So today is our 7th lecture. It's about stability and kinetics. And in this lecture, we're going to discuss some points about kinetics of reactions and about stability of drugs. Okay. Under kinetics, we'll discuss the points of law of mass action, the reaction order, zero order, second order, and third order kinetics. Zero first and second order kinetics, sorry, and then Calais-Menten equation and complex reactions. For stability, the points we'll discuss are factors affecting drug stability, physical stability, chemical stability, and microbiological stability. And actually, all these points are related to the next topic where we will discuss the applications of this knowledge that we need to know about the degradation of drug products and the rate of degradation. And then based on this study, we can determine the shelf life, which indicates the period of time where the drug will be stable and include or conform to the specifications that indicates efficacy and safety. So the aims of this lecture that by the end you should be able to define and understand the terms, drug stability, chemical kinetics, rate of reaction, order of reaction. Understand the law of mass action, know the kinetics of zero order, first order, and second order reactions, understand Calais-Menten equation, understand the complex reaction, describe the factors affecting drug stability, and understand what's the meaning of physical stability, chemical stability, and microbiological stability. And as I mentioned, all this will lead to understanding the basic concepts behind the concept of shelf life of drug products. Okay, so first let's know or define some terms to know the definition, like drug stability, chemical kinetics, rate of reaction, and order of reaction, or order of process. When we say drug stability, we mean maintaining the physical, chemical, therapeutic, and microbiological properties during the time of storage and use of the drug products. And when we talk about drug stability, we can talk about stability of active ingredient, we can talk about stability of drug product. So when we say stability of drug product, then we're talking about the stability of the pharmaceutical dosage form. There should be no physical changes during the period of shelf life where we can use the product. There should be no chemical changes. There should be no therapeutic changes, means the drug maintains its efficacy. It stays as effective as it was upon the time of production. And there should be no microbial changes, means there is no microbial growth or contamination, microbial contamination of the product during that time of storage. If any of these properties changes during the storage time, then it's not suitable for use anymore. Okay? Then in this case, we say the drug product is expired. Say it is expired. Chemical kinetics is the study of rate of chemical changes taking place during chemical reaction. Okay, why we discuss it when we talk about drug stability? Because degradation of drug products is a chemical reaction. Drug products may not be stable, may have some degradation. It may be, degradation may happen by different types of reactions, like oxidation, hydrolysis, and so on. So we study usually the rate of degradation, which is a chemical reaction of these drugs, and based on the knowledge about the rate of degradation, we can estimate the shelf life. We can estimate the time period where the drug content will remain within the accepted limit or accepted range. Okay. So, for example, many drugs can be used up till up till content of 90% of the labeled amount. Okay. When we produce the drug, the content is 100% usually. So if we study the rate of reaction of this drug, we can estimate the time period for drug to lose 10% and retain 90% of the content. The time for this 90% content is the expiry date, after which the content will be less than 90% and the drug should not be used according to the regulations. Okay. For some drugs, expiry date is when it reaches 95%, for example, and so on. So we can do the calculations based on the requirements of specific drugs. Okay, so we defined the chemical kinetics and we said it is the study of the rate of chemical changes taking place during chemical reaction. So what do we mean by rate of chemical changes? As we mentioned before, rate is when you divide amount by time. When you divide amount by time. So when we talk about rate of reaction, means the rate of change of the concentration of reactant or amount of reactant or a product with time. Rate is usually amount per time. For example, you say it will degrade by the rate of degradation, for example, is 5 grams per hour or per day, okay, or per year. So this is a rate of reaction, a degradation reaction of a drug, okay. Order of reaction or process, this is the power dependence of rate on the concentration of all reactants. We'll explain this one in the coming slides, but remember, order is the power. So, for example, if rate of reaction of certain substance is proportional to, usually we put is proportional to concentration. What is the power here? How much is the power? If we didn't write anything, then the power is equal to 1, right? The power is 1. So we call this one first order reaction. If reaction rate is proportional to square of the concentration, then it is second order reaction. If rate of reaction is constant, equal to a constant, then no concentration here, right? So if no concentration, then means the concentration is raised to the power how much to become 1? 0, right? So this one we call it 0 order reaction. So this one is not present because equal to 1. So order of reaction is the power dependence of reaction rate on the concentration of reactants. And this is identified by the law of mass action. So let's consider, for example, this reaction that substance A is reacting with substance B. The number of moles in the reaction for A is A small, for B is B small. And there is a reaction, reversible reaction as you see here. It will give number of moles C of product C and number of moles D of product D. The rate of chemical reaction is proportional to the product of the molar concentrations of reactants, each raised to a power usually equal to the number of molecules A and B of the substances A and B undergoing reaction. So if in the law of mass action, in such a reaction, we should write the rate of reaction R is equal to A raised to the power of the number of its molecules times B raised to the power of its number of molecules. Okay, here in this equation, we express the rate of reaction as formation, equal to the consumption of, since we depend on the concentration of reactants, with time, the concentration of reactants will decrease, right? So here it is expressed as the decrease in concentration of reacting substance. We can say, in other words, that rate of reaction is proportional to C to the power C small times D to the power D small and the reaction will be here negative sign. Here the concentration is decreasing with time. So here reaction is decreasing, here reaction is increasing. If you plot the first one, decrease in concentration, if you plot concentration versus time, the curve is going down. Here, if you plot the concentration of products with time, then the curve will be going up. So here the slope is positive, and here the slope is negative. Okay, the slope is negative. Simply, away from this equation, we said that reaction rate is proportional to a to the power a small times b to the power b small. And as we learned from mathematics before, to replace the proportionality sign with equal to, then you have to replace with constant. So this one we call it reaction rate constant. Reaction rate constant. Actually, this reaction rate constant is the slope of the curve. Okay, so if we use the concentration of reactants, this one is usually negative. But if we use the concentration of products, then K is positive. Okay, so experimentally, how do we study the rate of reaction? We start a reaction in a test tube, for example. It contained the drug product, the reactants. It contained the reactants A and B at certain concentration. And then we take samples. We take samples from this reaction medium every time interval, maybe every 5 minutes, every 10 minutes, depends on the speed of the reaction. And then we determine the concentration at different time intervals. Then we plot T against concentration versus time. And we draw the curve. Okay? The reaction rate constant is the slope, and then we can determine, based on the shape of the curve, we will explain later on, we can identify the order of the reaction, 0, first, second, or third order. If you want to determine the rate of reaction, which is the change in concentration per unit time, then you took a sample at 0 time. The concentration was 10, for example. This is the time, and this is the concentration. Maybe after 1 hour, the concentration became 8. So the rate will be during this interval. The first hour is 8 minus 10. Is how long? How much? 10 minus 8 is 2. You divide by the time interval 1 hour. So it will give you 2. For example, concentration unit milligram per liter per hour. You can do it in amount. You multiply concentration by volume, and then you determine the amount. And then you minus the amounts and you divide by time, then you get milligrams per hour. After 2 hours, maybe it became, say, for example, 7.2. Then the rate will be 8 minus 7.2, or say 7, okay? So 8 minus 7 is 1 divided by 1 hour, then 1 milligram per liter per hour, and so on. The rate of decrease in concentration may be fixed, then it is 0 order. If it is changing, like here, not the same amount every time interval, then it follows a higher order, maybe first, maybe second order, and so on. Okay? So if you have a simple equation for one product, just you are studying the degradation of a certain drug A, that will give a degradation product B. So then the rate of reaction, D is delta. means the small amount of product A consumed during a small time interval. So amount divided by time, this is the rate of reaction, is proportional to A to the power n, the number of molecules. If molecule is 1, then power is 1, then it is first order. Okay? N may be 0, maybe 1, maybe 2. So if it is 0, it is 0 order, means have fixed rate with time, doesn't change. But if it is first or second order, then the rate of change is the rate of reaction changes with time. It's not the same. Okay. So as we mentioned, experimentally, this is what we do. We plot the concentration instead of number of molecules. We can say the concentration of drug in certain volume. We plot with time. If we determine the reactant, then there should be decrease with time. The drug. If we determine the product concentration with time, then there will be a decrease with time. So you see here with time, time is passing. The black molecules for the drug, red molecules for the degradation product. So by the time the red is increasing and the black is decreasing, as you see by time. So when you plot the amount versus time, you can see that the reactant or the drug is decreasing, the product is increasing with time. So the rate of reaction can be the change in amount of drug with time or the change of the product with time. The drug is decreasing, so it has a negative sign. The product is increasing, so the rate has a positive sign. Okay. But if you look here, do you think the rate of reaction change with time or it is the same? Can you answer me? You can write in the text. What do you think here? The rate of reaction is stable with time or changing? What do you think? You can write changing. How did you know? Correct answer, the rate of reaction is changing with time. How did you know? Look at
Because
look at
concentration of B.
okay. How do you know that the rate of reaction is changing? It's not fixed. You look at the slope. Is the slope same or changing with time?
Changing.
See, it's changing. So here you have high slope. This fragment, the slope is less. Here maybe the slope is more or less. Okay. So this indicates there is a decrease in the rate of reaction with time. Okay. There is a decrease in the rate of reaction with time. But if it is zero order reaction, you have one slope, straight line. Slope is fixed. Okay. So this indicates a first or second order reaction. It's not zero order reaction because the slope is changing with time. So now experimentally, how to know if our drug, for example, or any process, if we study the kinetics of any process, we will apply this concept later on in the next year when we study the pharmacokinetics of drugs. So in this case, we will not study degradation of product in this subject. We will study the elimination of drugs or the time course of change of drug concentration in the body or in the plasma, in the blood. Okay? So here we study the kinetics of the drug in the body. We take, instead of concentrations of drug in reaction medium, we take the concentrations of drug in blood, and then we study the kinetics of the change of drug concentration in blood with time. Okay? So whatever the process we study, its kinetics, the methodology is the same. We plot a normal graph first. Okay, we plot a normal graph. And then we try to find out the shape of this plot. We try to find out the shape of the plot. So in zero order, as I explained to you, as you see here, what do you see? Usually zero order means fixed reaction rate, doesn't change with time. So you will see that the graph, the curve shape is like this, a straight line. And decreasing concentration with time, as you see here, because we measure the concentration of the reactant. And the equation of this line is usually what you know before from algebra, that y equal to, you can say a plus bc, a plus xb, or bx. Okay, so what is y? The concentration of drug, so that is y. Okay, and then what is a? A is the intercept, isn't it? This is the equation of the straight line. A is the intercept. So what is the intercept in this case? It is the concentration of the drug we study at time 0. That is the intercept. So we write the concentration at time 0. Plus B times X. X is the time. That is X, the time. Because we plot concentration versus time. B is what? B is the slope. And as I explained before, or mentioned, slope is equal to A. Here, the concentration is decreasing. K is always positive. K is always positive. So, since it is decreasing, then it should be minus K. Should be minus K. Okay? So, K is positive always. So, together with the sign, negative K here is the slope. So, say the slope is 0.2, for example, minus 0.2 should be minus. So, K is 0.2. And then the equation we write minus K time means minus 0.2 times T. Okay? So when you plot the rate of reaction, not the reaction, the concentration, the rate of reaction versus time, the rate of reaction is fixed. It doesn't change with time. It has the same value. Has the same value, doesn't change. So in this case, in zero order, rate of reaction is equal to A. It's a constant amount. So here we can calculate that Y is the concentration at any time point. We can write A at time t. So we can calculate the concentration at, for example, 2 hours. At 2 hours, then at 2 hours, for example, here, then how much is the concentration? We can determine it graphically by this way, and we can calculate it using this equation. We multiply the concentration at time 0 by negative K times T. So how about how much the rate of change? The rate of change is usually fixed and equal to the constant K. K is called reaction rate constant. Okay. But if you plot and then you find it is curved, then it might be first or second order reaction. Okay. So when the second order reaction give first order reaction, when it will give you a straight line, it will give you a straight line when you plot on the lone concentration versus time. So the second trial is if you get a curve, so you plot first, you get a straight line, it is zero order, you didn't get straight line, you try to see if it is first order. In first order, you plot lone concentration or lone A versus time. This curve will convert to a straight line. Okay? Then you can calculate the slope of this one. The slope will give you the K. And the reaction, the curve equation, that straight line equation, this linear relationship equation will be concentration at any time t equal to the concentration at time 0 times the exponent of negative kT. Where did I get this equation from? Because if I make ln A time versus t, then the straight line equation will turn to be ln A at time t equal to A at time, ln A at time 0 minus kt. That is y, that is intercept A, and that is slope times x, right? So now I want to remove the ln. So I make inverse ln. If I make inverse ln for this one, it will give me the concentration at time t. Inverse ln for concentration at time 0 will give you concentration at time 0. Inverse ln for negative kt or minus kt will give you exponent of this amount. Exponent, when we write in equations, and when you apply in the calculator, you make shift ln or inverse ln. Okay, so if you plot ln concentration versus time, you got a straight line, then this is the equation for the reaction, for the concentration change with time, and the rate of reaction here is first order, means it is concentration dependent. It is concentration dependent. So how far is it? It depends on concentration. It should depend on the concentration raised to the power 1 because first order reaction. So the reaction rate is equal to the concentration times the reaction rate, constant K. So from this equation, how to understand this equation? Okay, how to understand this equation? Originally, we wrote like this: reaction rate is proportional to the concentration of the drug. And we replaced the proportionality sign with equal to, and then we put constant. The constant we call reaction rate constant. Okay, so reaction rate equal to a constant times a variable, right? This A is variable, isn't it? So what happens to A with time? Does it increase or decrease? A is the reactant. So the amount of reactant and the concentration of reactant decrease with time. So the reaction rate decrease with time. So actually for this curve that you have high slope at the beginning, and then the slope became smaller, and the slope became more further smaller with time, means the reaction rate is decreasing. Why? Because the concentration is decreasing. So when we plot the reaction rate versus time, it will give us this amount. And the sign is negative. Reaction rate actually is decreasing. Okay. We don't need to put the negative sign to calculate the reaction rate value, but the sign means that it is decreasing with time. Okay, now we make this trial. We didn't still get a straight line like this. So means maybe second order reaction. How to identify if it is a second order reaction? Then in this case, we need to plot inverse of the concentration versus time. So you have a table, you have the concentration, you have time, and then you calculate ln A, you plot A versus time, you didn't get straight line. You plot ln A versus time, you didn't get straight line. Then you calculate 1 over A for each time point. And then you plot 1 divided by A versus time. If you get a straight line, then you have a second order reaction. This is the equation for the second order reaction. Y equal to intercept plus slope times t. Okay. Second order maybe not very important for We usually experience zero or first order in our studies, more common. So try to remember especially the first and zero order very well. Let's have examples from practice. This one we call it pseudo first order or pseudo zero order. Okay, this is the example of aspirin suspension. The problem is telling that a prescription for a liquid aspirin preparation is called for. It's to contain 325 milligrams per 5 ml or 6.5 grams per 100 ml. The solubility of aspirin at room temperature is 0.33 grams per 100 ml. Therefore, the preparation will definitely be a suspension because this amount is far larger than the solubility limit. So it will be a suspension. You add 6.5 gram per 100 ml, only 0.33 gram will be the salt. The remaining, which is 6.27 gram, will be in suspension form. And the pH of this product will be 6. The first order rate constant for aspirin degradation is 4.5 times 10 to the power negative 6 second to second to the power minus 1. Okay? So this is the K. This is the reaction rate constant of degradation of aspirin, K. Calculate the zero order rate constant. Determine the shelf life. And the shelf life here when the time to reach 90% of the initial concentration. The time to reach 90% of the initial concentration. Okay? Assuming that the product is satisfactory until the time at which it has decomposed to 90% of its original value. Means we allow only 10% decomposition. From 100 to 90% means decrease by only 10%. So now we say the reaction rate constant for first order. So how to calculate zero order? How this happens? Now the composition for the decomposition supposed to follow first order means it is concentration dependent. So why it will proceed according to zero order? Okay, why it will proceed to zero order? So this one not real zero order, actually it will be pseudo zero order. How it happens? Now you have a solution. Majority of the drug is already in suspension. And very little of the drug in solution. But which one will be decomposed? Only the solution, the dissolved part will be decomposed. Okay? We said that first order reaction rate is equal to concentration, to reaction rate constant times A. Means reaction rate is concentration dependent. Is concentration dependent. So if the concentration decreases, reaction rate will also decrease. But the question here, do you think the concentration decrease with time or no? Can you answer me? So now the information we are given in the problem that aspirin is a drug that decomposed by first order reaction. And the K, the reaction rate constant for aspirin degradation by first order is 4.5 multiplied by 10 to the power negative 6. The unit is second. So I understand from this one that the reaction rate will be dependent on the concentration. If the concentration decrease, the reaction rate will also decrease. So if I want to calculate, for example, you have the equation A equal to A0 minus multiplied by exponent of negative K T, right? So Actually, the time t, delta t, if you rearrange this equation, will be equal to ln C2 minus C1, but you change the, okay, C1 is A node, A divided by A divided by K. Okay, so if you want to calculate delta T according to first order reaction, this is the equation, ln A0 or A node divided by A. The first is 100. The second that we want T90, then this should be at 90%. 100 divided by 90%. And you divide by K. Then you get the time that it will take to degrade from 100% to 90%. But actually, this doesn't happen. It will follow zero order. Why and how to explain? The one that will degrade is only the one that is dissolved. Okay? So the 0.33 gram that is dissolved in 100 ml, 0.33 gram aspirin that is dissolved in 100 ml water is the only one that will degrade. But you have much more excess in suspension as undissolved parts, right? So any amount that is degraded will be replaced by a new amount that will dissolve. So most of the time, the amount degraded will be replaced by the amount dissolved. So the concentration is always stable at the solubility limit. So always the concentration will be equal to 2.33 gram per 100 ml. It will not change. Why? Because there is a big amount in suspension that if any amount consumed from the solution will be replaced by part of the amount in the suspension. So since the concentration will not change, the reaction rate also will not change. It will be stable. So the reaction rate will proceed at a very constant rate. The rate of reaction will follow this equation, R equal to the constant times A, but A will not change. A is always 0.33. So if you want to calculate the reaction rate is 4.5 times 10 to the power minus 6, that is K, times the concentration A, which is the solubility limit. That will not change because we have a lot of depot in suspension form that will replace the degraded amount. So here, this is the reaction rate. And the reaction rate here is gram per 100 ml per second. Okay. Then when we calculate time 90, the time for 90% to degrade, we set rate equal to concentration divided by delta time. So delta time will be equal to D concentration, delta concentration divided by the rate, isn't it? The change in concentration is 10%, which is 0.10 of the concentration, initial concentration. So initial amount is 6.5 grams. 10% degradation means 0.65 degraded, 0.10, 0.1 times 6.5. So this is the initial amount. This is the rate, the amount that will change, the change in concentration allowed during this time period. 10% only change. So it is 10% means 0.1 times the initial concentration. You divide by the rate that we calculated here. You divide by the rate calculated here. So this amount. Then you get the time in seconds. Take care of the units. Gram with gram, 100 ml with 100 ml. Second here means you divide by second to negative power, means you get a second with positive power, right? So it is this amount of seconds. We change today by dividing by 60 to get it in minute, and then you divide by 4 how many? 60 seconds to 60 divide to become minutes. And then you divide by 60 to get hours, and then you divide by 24 to get days. So at the end, you will get 5 days. You get 5 days. Okay? Actually, this is not one, this should not be maybe 10.5. This should, not 105, not 105. This one should be 10 to the power 5, I think. So double check the calculation. I think this one 10 to the power 5. Okay? But anyway, this is the calculation method. So you understand the concept here? The drug is supposed to follow first order reaction, and the reaction means rate depends on the concentration of the drug, but the concentration here will not change, will stay stable, because only the amount that is considered give the concentration is the dissolved amount, and still you have a lot of undissolved aspirin that will replace any degraded amount and will keep the concentration stable over a long period of time. So in this case, the reaction rate will be stable over time. Why? Because we have replacement and the concentration is kept constant. Okay, so this is the way to calculate the zero order reaction. If you remember here, in the zero order, we said that reaction rate is constant. Okay, is K. This one in case of zero order, but we said that in case of first order, reaction is equal to K times A. So here we proceed as first order reaction, but it is stable because A doesn't change. So all the time it will be this amount. It will be K times A. So it is a fixed amount, although it is a first order reaction. This one sometimes confusing. Did you understand the concept or no? We can repeat it again if you don't understand. Did you understand the concept? Hmm? Hello? Can I get answers? Did you understand this? Can you hear me?
Yes, doctor.
Do you understand, or I should repeat? Or anything you didn't understand all, or you didn't understand some? Can I get your feedback?
Understand, doctor.
Okay. Another example is the composition of hydrogen peroxide at 25 degrees in aqueous solution containing 0.02 molar potassium iodide. If we plot the concentration versus time when we add hydrogen peroxide to this aqueous solution, and we monitor the concentration over 70 minutes or 65 minutes, we can see that this is the curve we get. Looking at this one, is it zero or first or second order? Can it be zero order? Cannot, because no straight line. So the second thing we try to plot, as I said, long concentration versus time. Here we get a straight line. So this is first or second order. This is first order. Okay? So here the data, the raw data we get in our experiment. We decide that we will measure the concentration at time 0 at the beginning when we just mix them before mixing even. The initial concentration that we will get by mixing. Okay, so you just add to the mixture and take sample quickly, and then this is times 0, and then times, after 5 minutes, we take another sample. 10 minutes, we take another sample, we measure the concentration and so on, till, for example, 65 minutes. And then we make the plot. Time on x-axis, concentration y-axis. We didn't get straight line. This is not zero order. We make another table, another line, another column. We calculate ln concentration, and then we plot this ln concentration versus time. We get a straight line. So this is the degradation of it will show us the kinetics of degradation of hydrogen peroxide in aqueous solution containing this concentration of potassium iodide. It indicates it follows first order kinetics. So from this one, we get the equation of the curve. We find that equation is telling that y equal to, because the concentration is decreasing with time, means the slope will be negative. So equal to negative 0.0276 times x plus 4059. If we translate this equation to the way we wrote the concentration change with time, then we can write that it means that ln A equal to ln A naught minus K times time. And when we replace the value of K, then we say ln A equal to ln A naught minus 0.0276 multiplied by T. Okay, and we can write it another way without ln. We can say that concentration at any time equal to the initial concentration, which is A naught. This intercept, this is A naught. X multiplied by the exponent of negative 0.0276 multiplied by the time. So if I want the concentration at 2 hours, then I replace the time with 2 hours. I want to evaluate calculate for example, here we are using minutes. It depends on the units, take care. So here, what will be the unit of K? Since the time in minutes, what will be the unit of K? You will get a K equal to 0.0276 minute to the power negative 1. So here, time, when I use in calculation, should be also in minutes. So if I want the concentration at 2 hours, means I have to write 120 minutes. And in the time, I should substitute with 120 minutes. Okay? So take care of the units. So obtaining a straight line with ln concentration versus time plot indicates first order kinetics. As we explained, the reaction rate constant can be calculated from the slope. So slope is negative. You get the positive value only, it will give you the K. If you want to calculate the concentration of hydrogen peroxide after 80 minutes, then I use this equation. Just simply as I told you, A, the concentration at 80 minutes equal to initial concentration, which is how much? The intercept is 4.059, right? This is ln concentration or concentration? This is the ln of the concentration. You make inverse ln, you will get this value. Okay, so initial concentration is 57.9. So how about if I start with different concentration at time 0, then whatever the concentration you start with, you should write here. So equal to the initial concentration multiplied by exponent of negative K times T. So depends on the set of data you have. Maybe initial concentration is different, but just apply for the same. So this concentration was 57.9, so it will be equal to 57.9 times exponent of negative 0.0276 times 80 minutes, and then you calculate how much. You expect the concentration to be higher than 57.9 or lower than this amount? Should be higher or lower? Should be lower, because the concentration is decreasing with time, because the sign here is negative. Okay, so you get a smaller concentration. You cannot get from this data because the data is only up to 65 minutes. So if you want to find the concentration at 80 minutes, either you extend your line up till 80 minutes, or you calculate it using the equation as I did here. Okay, so these are first, second, and zero, first and second order study. But actually, not all the products will follow this single order kinetics. It may follow mixed order kinetics. So in some instances, the kinetics of pharmacokinetic process changes from predominantly first order to predominantly zero order with increasing dose of chronic medication. Okay. So here we talk about reactions that may happen in the body. A mixture of both first order and zero order kinetics is observed in such cases, and therefore the process is said to be or to follow mixed order kinetics. Means I have at some stage the reaction may follow first order, in another stage, or in another case, the reaction may follow zero order kinetics. Okay, so this one, in case if I study the change of drug concentration in the body, so that's why we call this one pharmacokinetics. Pharmacokinetics is the study of rate or the study of the time course of change of drug concentration in the body. We have linear pharmacokinetics and we have non-linear pharmacokinetics. So if the drug is following this usually first order kinetics, this is linear pharmacokinetics. But if it is following mixed order kinetics, then it is usually non-linear kinetics. This you will study in details next semester year when we study pharmacokinetics. But in brief, to explain to you what's the meaning of linear pharmacokinetics and non-linear, when you give different doses and then you measure the concentration in drug in the blood that is achieved with different doses. Some drugs will give you a linear relationship, means you increase the dose by certain proportion, you get increase in the concentration by the same proportion. So we call this one linear pharmacokinetics. Means that if you double the dose, you get double the concentration in blood. You triple the dose, you get triple the concentration. You half the dose, you get half the concentration in the blood. So this is a linear relationship, linear pharmacokinetics, linear relationship between dose and concentration. For some drugs, like this one that follow mixture of first order and zero order, they usually follow non-linear pharmacokinetics, means that at certain stage, there will be a more than expected increase in concentration with increasing the dose. Yeah, it means that at certain stage, maybe you double the dose, but you get 3 times the concentration. Okay, so in linear pharmacokinetics, dose is proportional to concentration, or opposite. Concentration is the concentration we get is proportional to the dose we give, is proportional to the dose we give. But in nonlinear pharmacokinetics, concentration is not proportional to the dose. Okay? So this kind of kinetics, the nonlinear pharmacokinetics, we call them dose-dependent kinetics. Because the proportion between dose and concentration change with changing the dose. You can see this curve. The proportion between dose and concentration change with changing the dose. So at certain stage, maybe the proportion is, say, 1 to 10, for example. Then it may become 1 to 20, then become 1 to 30, and so on. So the slope is changing, as you see. The slope is changing. So we call it dose-dependent kinetics. It happens sometimes in drug absorption, in drug distribution, and in drug elimination. Drug absorption because of capacity limited absorption means the drug will follow first order absorption maybe with more drug in the stomach, the absorption is faster, but maybe there is a maximum limit of absorption that beyond, if the amount is very high in the stomach, it will only be absorbed at a fixed rate. It will not be concentration dependent. Drug distribution, we talk about protein binding, for example. So maybe protein binding also have certain limit. So you increase the concentration, you increase protein binding, but if you increase the concentration above the limit, protein binding is same. It will not change anymore. Drug elimination, drugs like phenytoin, they are capacity limited metabolism. They are metabolized by capacity limited metabolism. So they are metabolized by certain enzymes. They are metabolized by certain enzymes. These enzymes have binding sites that will bind and react with the drug molecules, and they have maximum number of binding sites. So if the concentration is below that maximum capacity, so it will proceed according to first order, means that the metabolism rate, you can say instead of R, I will say M. Metabolism rate will be proportional to drug concentration, or subsequently proportional to the dose given, because, okay. And then if you increase the dose beyond certain limit, increase the concentration beyond the saturation limit, then it will not increase anymore because you already occupied all these binding sites. So after this, it will become zero order. In zero order, reaction rate is K, equal to K, it is constant. Okay. So below the capacity limit, it will proceed as first order. There is increase in reaction rate or metabolism rate with increasing concentration. Once you reach the maximum limit, then the reaction rate is not increased anymore, but will be at that fixed maximum limit. This kind of kinetics is named according to the scientists that they describe this mechanism. So we call it Michaelis-Menten kinetics. Okay. So here in Michaelis-Menten, this is the expression that you have enzyme E, and substrate, a drug. So, or any compound that, say, any biological compound that will be degraded by or metabolized by the enzyme system. So there is two steps. The first is they bind together, they form enzyme substrate complex, and then the reaction will proceed and they will make a metabolite or a product. Okay. So the first step is usually reversible. The second step is irreversible. We'll make a degradation product or metabolite. So in this one, we use usually steady state calculations. We have an equation that we use to calculate the reaction rate. The reaction rate or reaction velocity, V, here is equal to maximum velocity times the concentration of the drug or substrate divided by Km plus substrate. Okay. Km actually is the concentration of substrate at which V is equal to half the Vmax. Okay. So here, this is the equation for the rate of reaction. Can we have a 5 minutes break and then or just I complete this part about Michaelis-Menten and then we can have a break, okay? So complete the idea. So usually experimentally, when we rearrange this equation, we find that inverse of the velocity equal to inverse of Vmax plus Km divided by Vmax times inverse of the concentration of drug. So this is like the linear equation, y equal to intercept, which is A, plus slope, which is B, multiplied by x. So we plot 1 over V, this is y, versus inverse concentration. Okay? Then you will get a linear plot The slope is Km divided by Vm. That is the slope. And that is the intercept. Okay. And if you extend this on further, you can get the value of Km. This is 1 over Km. Okay. Michaelis-Menten kinetics is used for biochemical processes in the body involving metabolism of drugs. So we will use this one once we study the pharmacokinetics. When we study the pharmacokinetics of a drug like phenytoin, then to estimate the change in concentration over time, we have to use Michaelis-Menten equations. We cannot use first order kinetics equations. Okay. This drug follows nonlinear pharmacokinetics and follows Michaelis-Menten. Phenytoin is metabolism by capacity-limited enzyme system and follows nonlinear pharmacokinetics. So this is what we are going to use once we calculate the rate of, once we want to estimate the change of phenytoin concentration in the body or in the blood at any time after administration of the dose. Okay. Can we stop by this point? So we'll go back to talking about complex reactions. Many chemical reactions may not be just simply following simple zero, first or second or third order equations, but they can involve more than one step of reaction, and they may follow different rates, okay, or different orders, I mean. And these reactions are called complex reactions. They may be classified as reversible, parallel, or consecutive or series reactions. So, reversible reaction, as you know, there will be two directions of the reactions, forward and reverse direction. And there will be an equilibrium point. So when the ratio between reactants and products reach certain amount, certain ratio, then the reaction will be stopped. Then we call the reaction reached equilibrium. So both directions here may be first order, but the equation will be complicated because we have two reactions, actually, not one. We have A and B that give C and D. At the same time, we have C plus D that may give you A and B. You have forward and you have reverse reaction. We have parallel or side reactions where A will give B and C. It will follow many routes and pathways. So in the equation, you will have probably A, B, and C. We have series or consecutive reactions. A gives B and B gives C. So we may have equation for C and we have equation for B, right? So each step follows first order rules usually here and is not reversible. And it may be complex that have also some steps reversible and some are not. Okay. So for reversible reactions, the simplest reversible reaction is one in which both the forward and the reverse steps are first order process. Okay, so in reality, things may be more complicated. So the simplest one, both of them are first order. Equilibrium mixture of reactants and products. So as we said, the reaction will, at the beginning, you mix A and B, they will proceed, the reaction will proceed till you reach the equilibrium point. And at equilibrium, you have a mixture of reactants and products. So this means that not all the reactants will be consumed, right? If the reaction is A plus B gives you C and D, then at the end, there will be no A or B consumed. But if A plus B will be a reverse reaction, give you C and D. Then at equilibrium, you have all in the reaction mixture. You have A plus B plus C plus D, all present. Okay? The rate law is the difference between amount of the reactants at the beginning and at certain time equal to the products. This is if, for example, we say A is giving B. So here the rate law is A node minus A. A node is the concentration at time 0. A is the concentration at any time t. The difference between them is usually equal to the amount of product that has been formed. And the amount of product at time t. T is subscript here, not multiplied by t. B at time t. B at time t. Okay. At equilibrium, there is, we call A equilibrium. This is the concentration at equilibrium. You see here the concentration for the change in the concentration, the equation for changing concentration with time became more complicated. Okay. Became more complicated. So instead of 1K, we have 2Ks, reaction rate constant for forward reaction and for back reaction times T. So ln, this is about first order. Huh? Both are going in the direction of both reactions, forward and backward, if they are first order reactions. Then ln initial concentration minus equilibrium concentration divided by the concentration at time t minus equilibrium concentration equals to Kf plus Kr times T. Okay? So if you want to get rid of ln, then you get inverse ln. Then here this will be exponent. So you can write it that this part only is equal to exponent of Kf plus Kr times T. Exponent of this part. Here the reaction rate constant is usually Kf divided by Kr minus concentration of product at equilibrium divided by concentration of reactant at equilibrium for that simple equation. If you have more products and more reactants, then you have more complicated equation. And this is the plot of Y. So if you go back to this reaction, so this is Y equal to slope times X. Is there any B in the equation? No B in the equation. So what's the value of the intercept? Since no intercept, the value is 0. So the plot will be at time 0, you have no. This value is equal to 0. And then it will increase with time. Okay, how did we get it? If we plot log, then log any amount. Okay, how to say it? Log how much equals 0. If I say to you, if log x equal to 0, so how much is x?
Ya Allah, itu difficult tidak? Difficult sih.
How much is X? How much is X? No. Okay. How much is X? Okay. 10 to the power 0 equal to how much?
1.2.
Correct.
Yeah.
So X equal to
1.
1. Log 1 equal to
0.
0. Okay. Now, how the amount is 1? At time 0, the equation A at time 0 minus A at equilibrium divided by A minus A at equilibrium. How much is A here? At time 0, A is equal to A node, right? At time 0, the concentration is equal to A node. The value of this amount, how much? Equal to 1, right? We say the equation is, I repeat again, okay. Let's clean this one first. The equation is y equal to slope times t. Okay, now I want to calculate the concentration at time 1 hour, assuming that k in hour to the power negative 1. Okay, let's follow this one. It is in minutes. Okay, assume k in the unit of k is minute to the power negative 1. Assume that you want to calculate the concentration at 10 minutes. Then here this one should be the concentration after 10 minutes, right? Here this will be at concentration after 10 minutes. This one's still the initial concentration. And time should be equal to how much? 10 minutes. This is what will you replace in the equation, right? But how much is the value at time 0? Time will be equal to 0, not 10 minutes. And how much will be the concentration A? Will be the same concentration at time 0, right? So you should write at time 0, concentration at time 0 is actually A node. So this the value of this fraction became how much? Became 1. When you calculate log 1, then it will give you 0. Okay? You got it? So here, stereoisomer, the change in the stereoisomer form, we call it epimerization. This is a reversible reaction happened to iso 7 chlorotetracycline when we put in dimethyl formamide containing sodium dihydrogen phosphate at 25 degrees, means at room temperature, when the concentration is 1 molar. They find that there is an epimerization change in the stereoisomer from one form to another, and the rate of reaction follows this. The reaction or the concentration follows this equation that we just explained. That ln. So this indicates that the reaction here is reversible and is first order in both directions. Okay. Another reaction is, here we mentioned about chlorotetracycline, I7 chlorotetracycline. Also, there is a reversible isomerization of tetracycline at pH between 2 and 6, acidic pH. Epimerization occurs resulting in epitetracyclines, which has less therapeutic activity than natural form. Under acidic condition, the natural compound A is converted to epiisomer B. So this is the tetracycline, and this is the epitetracycline. So what is the problem of such a polymerization reaction? It will lead to loss of therapeutic activity. So the drug may not be effective. So we don't want this to happen. We want to keep it at conditions where this reaction doesn't happen. And this is a reversible reaction, means that it has some equilibrium point, it will stop back. Okay, now we talk about the parallel or side reactions. This is common in drug systems when organic compounds are involved. Example, prednisolone, a corticosteroid, you all know. It degrades in sodium hydroxide in alkaline medium. So we call this alkaline, you can say degradation or hydrolysis, alkaline hydrolysis. So dihydroxyacetone side chain will disappear. This is the one that will react. And actually, it follows parallel pseudo first order reactions with appearance of acidic and neutral steroidal products. So there are parallel reactions. It forms degradation will follow two pathways. One of them will make acidic degradation product, and the second one will make neutral degradation product. Each of it has its own reaction rate constant. But when you write the equation, when you want to calculate the degradation rate, it will not be the simple, if it follows only one pathway, then I can just write it in the previous equation that we saw that, for example, concentration of P at any time will be equal to the initial concentration of P. Let's write it P instead of A. Concentration of P at any time equal to the initial concentration of P, means the concentration at time 0, times the exponent of K times T. Okay. Here we don't have one K, we have two Ks, K1 and K2. So the equation must contain both. So here the rate of reaction, the change or the decrease, we make it minus, negative. D is fraction or small part, delta P divided by the delta time, means at certain time interval. So amount change in the amount of P at certain time interval means the rate of degradation of P is equal to K1 times P plus K2 times P. Okay, so then this is an old equation, that is rate of reaction is proportional to actually K times P, but K here is equal to K1 plus K2. Okay, because you have two reactions containing simultaneously. And here, if you want to calculate K1 alone, K2 alone, then you have different equations. K1 is the slope times K, not the slope only, it's the slope times K divided by P naught, and same for K2. And the equation to give the change in the amount of one of the products with time is that, of course, here it is plus because the amount increase with time. This is a product, not reactant. Okay, so it's not minus, it is plus. So you see the reaction. You don't need to memorize the equation, but you need to understand it, that you have more processes, then the equation that will be used to calculate the amount of reactants or concentration of reactants or concentration of product at any time point will contain more variables, will be more complicated because you have more than one process going on at the same time. So here you have K1, K. Okay? Why K1? Because K1 is the the reaction rate constant for forming A. If you want to calculate for N, then you will turn it to K2. Okay, you will turn it to K2. A plot of concentration A or N against, so here this is the X and this is the Y. So when you plot A or N versus 1 minus e to the power kt, then A concentration, of course, should increase with time, then it will give a straight line. And then what will happen? The slope will be equal to this amount. And this will be the intercept. Okay. Example of parallel side reactions also hydrocortisone. Stability of hydrocortisone in aqueous. Aqueous means dissolved in water, and in oil vehicles, in ointment bases, and in emulsified vehicles at elevated temperatures and various degrees of acidity and basicity is studied. It is unstable at room temperature in aqueous vehicles if the pH is basic. It is unstable at room temperature in alcohol, unstable in glycerine. Alcohol and glycerine improve stability. Okay, so it is unstable at room temperature in aqueous vehicles if the pH is basic. Alcohol and glycerine improve stability. We'll explain in the coming slide. When we talk about stability, we'll explain why using co-solvents will improve the stability. Okay. Unstable also at elevated temperature in highly acidic and basic media. And here they follow pseudo first order reaction. Here they follow parallel scheme in the degradation. Okay. Pseudo first order and pseudo second order parallel reactions, how they happen when a reaction pathway involves both pseudo first and pseudo second order pathways. Then we use these equations. Okay. As we said, depending on the number of molecules in the law of mass action that we said at the beginning of the lecture, then, for example, here, one molecule gives one molecule, then reaction rate is proportional to, in this equation, the reaction rate will be proportional to K times D. Drug will give product, degradation product. But here, the reaction rate will be proportional to, so no proportional, sorry, since we say K, then equal to. Here would be equal to K times D to the power 2. Should be equal to the raised to a power equal to the number of molecules. So this is, the power here is 1, this is the first order reaction. The power here is 2, this is the second order reaction. Okay? So if we have a parallel reaction, then we have both first and second order, this is the equation. Okay? Why we call them pseudo and second and pseudo first? Because the reaction doesn't occur according any one of them alone. The reaction occurs according to both together. The total reaction rate according to both reactions. It is a parallel. One is second order and one is first order. And give two products, product 2 and product 1. Okay? So here second order and this one is first order. So it doesn't proceed according to this or this. So we call it pseudo first and pseudo second order parallel reaction. And example is degradation of ampicillin. Ampicillin gave two products. One molecule of ampicillin will give one molecule of alpha aminobenzyl penicillinic acid. Together to give ampicillin dimer. product 2. So this one is a second order reaction and occurring at the same time simultaneously with a first order reaction. So this is the increase in concentration of product 2 with time. This is the increase in concentration of product 1 with time. This is second order, this is first order. Okay? But here the curve for the total rate of decrease of the drug product with time. It should be this one at any time point. Okay? The rate of decrease is equal to the rate of increase. You change the sign, of course, from positive to negative, equal to the rate of formation of P2 plus the rate of formation of P1. Okay, and you change the sign. So this will give you the total. So actually, it's not following the total rate of decrease in concentration of ampicillin doesn't follow either pure second order or pure first order. It follows a mixture of both. That's why you call it pseudo first and pseudo second order reaction, parallel reaction. Okay. We may have complex reactions that contains one-way direction reactions and reverse reactions. Okay, so it contains reverse and not reverse at the same time. So maybe this is what we show in the substrate, for example, but it has additional direction. So you have a drug D and A, they will react together to form a reaction complex. Okay, and then this reaction is reversible and has equilibrium constant. And in this direction, after this complex formation, then product 2 will be formed. This is following maybe first order reaction. And then also there is another parallel reaction that D and A will form product 1. So you can write like D plus A. We have two arms. One of them, they will form product 1. One of them, they have reversible direction. They will make a complex D A, and this will form product 2. So you have parallel reaction. But one of them is reverse reactions. So this case happen or obtained when a drug D forms a complex DA with A, which is defined by the equilibrium constant K, and both D and DA are capable of undergoing independent pseudo first order reactions. When the concentration of A is significantly higher than that of D, the kinetics can be described by equation, then became more complicated. Okay. This one, the change in the amount of D and the amount of the complex is equal to the constant of first and second reaction. Okay. So here, why we didn't have anything talking about equilibrium? Because we mentioned that this one assumes that it is one direction reaction. If you refer back to the previous slides, it is same equation like with no equilibrium in the middle, just a parallel reaction in two directions, no reverse. Okay, why? Because we give a assumption that A is significantly higher than D. So in this case, there is no this will drive the equation always in one direction, the reaction always in the forward. It will drive the reaction in the forward direction. Okay, if one is significantly higher than the other. Okay, how about if A is not significantly higher than D, then in this case the equation will be much more complicated. Okay, example from this series of Here, actually, what do you have here? What kind of reaction? It is parallel and at the same time it is a series reaction because we have consecutive steps. Step 1, step 2, step 3. So the complexity of this reaction is that it is parallel and at the same time it is a series. One of the arms is a series reaction, right? Example here is the degradation of glucose in acid medium. Glucose may have a reverse reaction. It will form polysaccharides and one first order, one direction reaction, forward reaction that will form 5-hydroxy methyl furfural. So this is step 1. And then this one here become more complicated, that this second reaction, step 2, different materials, colored materials, and formic and levulinic acids. So see how complex reactions may be. You may have, so what do you have here? You have two parallel steps and one reverse. One of them is reverse reaction, reversible reaction, okay? So series or consecutive reactions, they may have all complex reactions, like this example, may have reversible, parallel, and consecutive processes. So this is an example. We have reversible. Here we have parallel. And here we talk about consecutive reactions. Okay? And you end up with concentration of glucose. The change with time is complicated equation because we have several rate constants. Okay? So nothing much to explain about glucose. We move to drug stability. Definition of drug stability, if we say the drug is stable, means the drug is still keeping its original properties. It's not changed significantly, so still active and effective and safe. The standard definition as per United States Pharmacopoeia defines the stability of pharmaceutical product as the extent to which a product retains within specified limits and throughout its period of storage and use the same properties and characteristics that it possessed at the time of its manufacturing. So at the time of its manufacturing, not manufacturer, should be manufacturing. Okay. So what does it mean? We have limits. So it retains within specified limits. For example, when I talk about the drug assay, I say, for example, that assay should be between 100 to 90%. Okay? So during, maybe once I produce it, it is 1 plus or minus 100%. During the shelf life, the period of storage, it should not be less than 90%. So it should be more than or equal to 90%. If within this limit, then I say the drug is stable. Below this, I say the drug is not stable. Not stable means expired, cannot be used anymore. Okay? And this applies for the other tests that I do for the product as well, microbiology, other things. So the period of time that it will retain the characteristics, including assay, dissolution, disintegration, whatever, physical characteristics or biological or microbiological or chemical, if it retained it within the accepted limit, then the drug is called stable. And this period of time where it is within the accepted limit, I call it the shelf life of the product. After the shelf life, stability is, or the performance is outside the acceptance limit. We don't say the drug is stable at this time and we call it expired. We call it expired. So why we need to study the stability? because it provides the evidence on how the quality of the drug substance or drug product varies with time under influence of variety of environmental factors, such as temperature, humidity, and light. So on active ingredients and on finished drug products, we perform stability studies. So I perform testing for the product and I see how the chemistry, microbiological, and physical characteristics change with time. And the time that all these characteristics remain within the acceptable limits, this will be the shelf life of the drug. Okay? It will help to understand the difference. I can study the stability under different conditions, under different temperatures, temperature degrees, under different humidity values, under light and in darkness, and I see the effect of all these factors. If I found that my drug, for example, degrades quickly if exposed to light, then I should protect it from light. I have to use a good, suitable packaging that will protect from light. Okay? This will establish also a retest period for the drug substance of shelf life. So if you talk about active ingredients stability study, I can know the period of time that I should retest the drug before I can decide whether to use in manufacture or no, based on my knowledge of the degradation rate of this drug product, this active ingredient. For drug products, I can estimate the shelf life, for how long the drug can be suitable to be used after manufacturing. Okay. And also I can recommend the storage conditions. As I mentioned, maybe my drug, I find that it is affected significantly by humidity. Then I should use a suitable packaging that protect from humidity. I should advise not to keep in a humid place. My drug is not stable at room temperature, then should be refrigerated. My drug is not stable if exposed to light, then I should put, for example, an amber glass or in a dark plastic blister so that it will be protected from light. So this will ensure that my drug has the required efficacy and safety. This final, I determine the shelf life for the drug, not change it, so it's still effective. Didn't degrade, give toxic degradation products, for example, doesn't have microbial growth, so still safe to be used. So as I told you in the previous slide, we perform stability studies on drug substances and on drug products. So drug substance is the unformulated drug substance. We call it API or active pharmaceutical ingredient. Maybe subsequently formulated. I add some excipients to it to produce the dosage form, to make tablets, to make suspension, syrup, whatever, or ointment from it. I mix the active pharmaceutical ingredient or drug substance with excipients, suitable excipients to make the required dosage form. When we talk about drug product or finished drug product, this is the dosage form with the final immediate packaging. Usually we add the word finished product, finished drug product. So this one will be in the final packaging. Okay, here in the definition they say immediate packaging, not all the packaging. So still not finished. Immediate packaging means, for example, it is syrup, then you put in a syrup bottle, then it become a drug product. Okay, but if you still put the label, you put in a carton box, this is the final form that will reach the market, then I call it finished product. So let's go across the factors affecting drug stability. There are the main factors, as we mentioned, is temperature, humidity may affect, or moisture, light, and also pH of the medium. Okay, so moisture, light, and also the type of dosage form, and last thing is the excipients used, which is drug incompatibility, excipient or the packaging. So talking about temperature, usually decomposition of the drug is a reaction, degradation reaction. The reaction is usually is accelerated with use of temperature. So the higher temperature, the higher the degradation rate, which may occur by oxidation, reduction, hydrolysis. So this will lead to drug degradation. So higher temperature means less shelf life. Okay. Second is the pH. And the pH is significant, especially when you have liquid or semi-solid dosage forms. In solid dosage forms, pH will not be that effective, and we don't usually have extreme pHs in such case. No solution, no measurement of pH, right? pH means depends on the activity of ions in the aqueous medium. So if you don't have aqueous medium, don't talk about pH. Okay, so when we talk about pH effect, when we talk about aqueous formulations only. So acidic and alkaline pH usually affect the rate of decomposition of most drugs. Most drugs are usually stable between pH of 4 and 8. But how much is the suitable pH for certain drug? This you have to study. Not all drugs will be suitable at the same pH. You may formulate certain drug at pH of 7, it will be stable. Another drug may degrade, may be more stable at alkaline. Another drug may be more stable at acidic medium, and so on. So there is difference between drugs in the suitable pH that for stability. Usually drugs will react when they're ionized, and they will be ionized depending on whether they are weak acid or weak basic. They will be ionized in opposite pH. So if they are weakly acidic, you put them in alkaline pH, they will be more ionized. More ionized, they can react. So they decompose faster when they are ionized. Okay? So if the pH of drug solution has to be adjusted to improve, the problem is to be soluble also need to be ionized. So you want to increase the solubility, you adjust the pH to make it more ionized. You make it more ionized, then you have ionization reaction. That drug, for example, the drug is composed of AB, say A is negative and B is positive. This is ionic product. Can be ionized, sorry, okay, to give A and B, and this is reversible reaction. When you play around pH, then you can increase ionization or decrease. You want to shift the ionization equilibrium. So it depends on the pH. At certain pH, there's equilibrium between both. At certain pH, you shift to forward direction. At certain pH, you make it non-ionized. So if it is weak acidic, you make it alkaline, then it will not ionize. It will ionize, sorry, more. But if it is weakly acidic and you make pH acidic, it will not ionize. Now we want to dissolve. So acidic, I will put in basic medium. It will be more ionized, it will dissolve, but it will decompose faster. So you have to choose a point of pH where you can dissolve, but degradation rate is not very fast. You can keep it stable within the shelf life. The other option is, as I mentioned in the previous slide, I told you I'll explain later about glycerin, propylene glycol, and these co-solvents. They can be used so that we don't rely on pH adjustment for solubilization. So we can improve the solubility by using water miscible solvent, not by adjusting the pH. So some solvents like propylene glycol or alcohol or glycerin, we can add them as, we call them co-solvent, means we have water and we'll have propylene glycol mixture with it, or we have glycerin with it, or we have alcohol with it in the medium. So this solvent will help to solubilize the drug product, and it will also suppress the ionization, reduce the pH required to achieve solubility, the extreme pH. It will enhance the solubility at the same time without adjusting the pH to make it very ionizable. They reduce water activity by reducing polarity of the solvent. For example, if the solvent contains 20% propylene glycol, the rest is water, and you used it for dissolving chlordiazepoxide to make injection for this purpose, then you can solubilize chlordiazepoxide and you stabilize it also. It will not degrade quickly as if you change the pH to solubilize this one. Okay. Now, if you go to moisture, you know that for the drugs to react, they must be in solution. So if you have moisture, it will catalyze chemical reactions such as oxidation, hydrolysis, and reduction reaction. And also water will promote microbial growth. For microbes like bacteria and fungi, they need an aqueous medium to grow. So for example, with dry products like tablets, you will not need any preservative. But if you have a syrup contains high concentration of sugar, it is as a preservative. But if you have, for example, water, aqueous injection, and then for example, or aqueous solution that doesn't have high concentration of sugar, then you need to add preservatives so that you prevent the growth of microbes, either bacteria or fungi. Okay, light also affect drug stability. Not all drugs are light sensitive, but some drugs are light sensitive. Light will provide the energy or thermal effect, which lead to oxidation and means degradation of the product. And finally, the dosage form itself. You have a liquid dosage form, it is less stable compared to solid dosage form. So same drug, if you make it as tablet, it may be stable for 5 years, but you make it as syrup, it may be only stable for 2 years. Why? Because rate of degradation is faster when you have an aqueous medium in the presence of water. Last thing is drug incompatibility. The drug may react with the excipient in the formulation or may interact also with the package material itself. So we have to study this one to improve drug stability. Last thing is exposure to oxygen. They may affect the drug stability. Some drugs may be oxidized easily in air. So we have to protect from air, or we have to add some antioxidants in the mixture so that they prevent oxidation. So we have to do stability study. We have to expose the drug product or drug substance to several factors, and we study their degradation and study or understand what are the optimum conditions to stabilize the drug, reduce the degradation of the drug so that we increase their chemical stability. And we also, if there is microbiological instability, we have to use preservatives to prevent growth of microorganisms. Maybe you can stop by this slide now because the time finished. And the remaining slides we can discuss in the coming lecture with the coming lecture slides. Okay? Any question up to this point? Do you have any questions?
No.
Okay.
No.